Hi, welcome back to INST 314, Statistics for Information Science, with your host, Shawn Janzen. We're continuing our talk on Inference Part 3 with the normal distribution, z-scores, and confidence intervals, and we're expanding these topics into hypothesis testing. And in previous videos, you probably heard me say things like left tail and right tail, upper and lower. And this is where we're really going to dig into what those topics mean and what it means for our hypothesis testing as we get into what we call directional hypothesis testing. So let's go ahead and get started with a talk on the inferential framework. Remember that the concept of the null hypothesis is that we say that there's no difference, no change, no relationship, no effect with the null hypothesis. Null, think of it as zero, or nothing. So then what we're trying to say is that given a certain statistical value, what's the probability that the value we have is so great that it's not by chance alone? Okay, so more specifically, we're trying to find a probability we observe in our sample given the null hypothesis being true. And if the probability is so low, then it's probably not, the initial assumption that there's no difference is probably not true, and that there is indeed a relationship. So we are trying to disprove this null hypothesis. And in inferential statistics, there's generally two ways we can go about doing this: hypothesis test and confidence intervals. And I've been playing a little fast and loose and mixing these things up, but they are indeed two different approaches to determining if we can reject the null hypothesis or not. So let's go ahead and recap some hypothesis testing. We said before that the null is the base level, the no change, no difference. The alternative is the opposition, that there is a change, a non-zero, and that we're always talking about the population, never the sample in this regard. We use the sample to talk about the population. But the population data remains unknown, and we have to infer it from the sample. I gave you before the idea of the speed limit, where our speed limit is alpha. This is the maximum level of risk we're willing to take, and the p-value is how fast are we driving. And if your p-value, your driving speed, exceeds your alpha, your speed limit, then you run into the area where you are you could be in trouble with the stats police, and you are then not going to be statistically significant, and you fail to reject the null hypothesis. Whereas if you are under the speed limit, you are statistically significant, and you're all right. I also said before, at least in class, where we can contrast these two, that they're two halves of the same coin if we compare alpha and p-value with the observed statistic and its critical value. That a critical value has a probability of occurrence, and that probability of occurrence is alpha. And the statistic has a probability of occurring, and that's our p-value. And on any distribution, when we look and we're trying to get the values out into the far ends of the tails tend to get smaller. The chance of getting out into that tail is smaller, and so therefore, if a statistic is larger than its critical value, it's farther out into the tail, it's statistically significant. Likewise, if a statistic is large, it goes farther out in the tail, the probability of it occurring under that null distribution is very small, and therefore smaller than the p-value, and also statistically significant. So let's go ahead and see this a little bit more visually. Here is the shape of a null distribution that we assume is true. I have a blue shaded area in the upper right hand tail that says this is the chance of a value occurring. It gives us a critical region. Let's go ahead and talk about directional testing now, though, because this is really part of the focus on this area here. Now, with an alternative hypothesis we said before, it's simply no effect, or a non-zero effect. Rather, a non-zero effect. And when we go into directional testing, we can actually split this up and say that you can have a test that's one-sided or two-sided. Now, a one-sided test, you only care about if something is less than or greater than a certain value, such as if a certain candidate being elected is going to get more than 50% of the votes. A two-sided test is if you only care if there is a difference. We don't care if that difference is greater than or less than, that there's simply a difference. And if we're going to graph this out, we would see that each one has a null distribution, just a normal distribution. And in a one-tail left tail test, or lower tail test, we would be looking for a critical region on the left side of the normal distribution, and we're going to color that in that left tail. If we're doing a right tail one tail test, or right tail upper one tail upper test, then we're only concerned about the right side of the distribution, and we're going to shade in that right tail upper side. If we're looking at a two-tail test, this is where we are only concerned if there is a difference, we don't care if it's in the top or the bottom, then it's going to get shaded into both sides, left and right. but it comes with a little bit of a cost, and we'll talk about that soon enough. So when we talk about this in symbol form, which appears above the distributions here, we have our H sub zeros or H naughts. Those are our null hypotheses. And in each of those cases, we say that mu is equal to the mu zero or mu naught. And so they're the same. And H1 is our alternative, or HA, if we wanted to write it differently. And in the one tail left, mu is less than mu zero. So our sample mean is less than the population mean that we're expecting to find it. Now, I shouldn't say sample. The population mean is against the theoretical population mean of 0. And in the upper right tail, mu is greater than mu naught. So we assume that the population mean is greater than our null population mean. And in the two-tail version in the middle, instead of using a less than or greater than sign, we use a not equal sign to say that it is simply different from our null mean. And we're going to go ahead and talk about this a little bit more in terms of their powers. One tail has more power to detect a particular statistical effect. And the benefit of this is it only tests in one direction. Well, I guess that's a drawback, because if something's happening on the other side of the tail, you don't get to see if it's causing a statistical difference, but at the same time, you don't care. You're only concerned to see, is there an impact on the tail in which I'm looking for? And because all of your attention is focused in that one tail, you have more power in which to see it. But if you're looking at a two-tail test, you have less power because you're splitting your attention. Think of if you had to watch one thing, like one TV screen, and then I give you two different TV screens, not next to each other, and I said, watch them both. You're going to have to keep moving your head back and forth, and you're going to split your attention and your resources. So it's less powerful to see what's going on, but the advantage is you can test for a direction on either side. So they both have trade-offs. And so if we're looking at these in terms of density, what I have on the screen for you here is just a normal distribution with the right tail shaded in, and we have it at 95% with an alpha of 0.05. If I go ahead and flip this, now we have a normal distribution with an alpha of 0.05, but it is two-tailed. And so where before we had that red shaded region started at probably a 0.95, now our right tail starts at 0.975, but we also get a left tail at 0.025. And so the probability is less in the upper right-hand corner than it was before with the upper right tail test, but we've gained some critical region on the left side. Whereas if we shift this into a graphic where we can go ahead and compare, I've drawn a vertical line straight down where you can see how much smaller the two-tail red critical region is on the upper side than it is with its upper one-tail compatriot with. They're both alpha 0.05. Keep this in mind. Same level of alpha, but one is a one-tail upper test and the other one is a two-tail test, and we can see how the critical regions are split. So let's go ahead and give a brief example of this. A one-tail hypothesis would ask a question like, does improving lunches at school improve children's academic performance? A two-tail hypothesis would say, does improving lunches at school affect academic performance? Keep in mind, when we go ahead and look at this, the one-tail hypothesis says we're just looking to see if there is an improvement. So if the average child's academic performance was, let's say, 2.3, and we had some hypothetical value, that we had a score of 2.8, we could say then, is this 2.8 greater than? We're looking to see, does something improve? And so the two-tail might say, is there simply an effect? If we had a sample mean of 2.3 and we had a statistic that we thought might be 2.8, we just want to know, does it have an effect? Is it higher or lower? We would change that greater than sign to a not equal sign, because we could be looking for an effect that's larger or below, because maybe providing school lunches decreases academic performance. Most researchers would say otherwise, but in a two-tail, we would be looking for both directions. And if we're going to put this into a hypothesis test, we could say we have an alpha of 0.05 with a sample of 100 students, standard deviation of 1.2. We plug this in, and we have our sample statistic of 2.8 minus the population mean of 2.3 divided by the standard deviation of 1.2, square root of 100, gives us a z-score of 4.17. We can go ahead and take that and plug it into the p-value, and the p-norm function. It will give us the p-value, and it gives us a ridiculously small value where a p-value is less than 0.001. So what can we go ahead and conclude? Go ahead, pause a minute to think about it, and let's come back. So what we can go ahead and conclude is that with a p-value of 0.001, it is highly unlikely that we're going to get a z-score of 4.17 if the null distribution, which has a mean at 2.3 for the student's academic performance, is true. It is highly unlikely that we get that z-score. Therefore, it is highly unlikely that the null distribution that we have is true, and therefore we are going to reject that null hypothesis in favor of some alternative that it is potentially having a mean at 2.8 instead of 2.3. Let's go ahead and talk about this briefly in terms of normal distributions and power analysis. So we said before that when you're dealing with power analysis, you get to do things like effect sizes, which we're going to use as D, sample size, which is an N, significance level, which is our alpha, and then we're going to include the alternative. Are we looking at a one-tailed test or a two-tailed test? And we're going to indicate the power of the test that we want. So we're going to use R. We're going to use the PWR library where our power tests are called, and the function we're going to use is pwr.norm.test. And so inside there, we specify we're going to use the same French fry size as we had before. So if I want to have an effect of 0.5, a sample size of 100, a sig level, that's my alpha of 0.05, I'm going to indicate I want a greater, which is what I need to use for a one-tail upper test. And then I'm going to leave null as my power. I'll go ahead and run that, and it tells me that I have a power of 0.9999. What does that mean? That means I have a power that if there is a difference in my study here, that having a large effect of 0.5, a sample size of 100, alpha 0.05, and it's a one-tailed test, that if there really is a difference to be found, that I'm going to find it 99.99% of the time. And that's a really strong power. And with that, I'll let you go, and I'll see you in the next video.